Alright, the last thing we're going to have a look at in our further integration topic for extension 2 is working further with the definite integral. So some important things to realise that might be obvious that we've all seen in advanced in extension 1 is, first of all, areas above and below the axis. So areas above the axis are positive and areas below the axis are negative, which means if you want to know the area below an axis, you need to take the absolute value. Of course, nice and easy, the difference of two functions is going to be the higher function minus the lower function every time. Of course, that deduction from the fundamental theorem of calculus is that we can split integrals into two different integrals. So the integral from 0 to 3 of a function is the same as the integral from 0 to 2 plus the integral from 3 to 2 of the same function. Then what we can do is switch the limits. So the integral from a to b of f of x dx is just equal to minus the integral from b to a of f of x dx. And something that you mightn't have seen but's quite obvious is that we can change variables. You know, the equation y equals x squared is the same thing as the equation y equals t squared. We've just changed the x-axis from x to t. So the integral from 0 to 2 of x squared plus 3 dx is just the same as the integral from 0 to 2 of u squared plus 3 du. It would give you the same answer at the end. Of course, it's different if it was an indefinite integral because you'd have different pronumerals in the answer. But in this case, it's the same if you're finding a definite integral. Odd and even functions, something again that we saw in advanced. The integral from minus a to a of an even function is just two lots of the integral from 0 to a. And for an odd function, the integral from minus a to a is 0. Some other important things. When we're multiplying functions, an even times an even is an even, and so on. There's different things here. And as well, if we want to transform our functions, so if I've got the integral from 0 to 2 dx if the equation was x squared plus 3, if I moved that parabola to the side by 3, by applying this transformation, well, the integral now from 2 plus 3 is 0 plus 3 is 3, and 2 plus 3 is 5 would be the same, because I've just moved the parabola over, which means the area with the x-axis remains the same. So, example number 1 is to prove that the integral from 0 to a of f of a minus x is equal to the integral from 0 to a of f of x dx, and hence find the integral from 0 to pi of x sine of x dx. So to do that, we're just going to realise that, okay, we're looking at the integral from 0 to a of f of a minus x dx. Okay, let's do a u substitution. Let u equal a minus x, because a minus x is just a variable in the equation. It's whenever we see an x, we're replacing it with a minus x. So we can do a u substitution here. Du is equal to minus dx. So this is equal to the integral from 0 to a of f of u du times by minus du, sorry. But the integral of a negative thing, it's just really going to be the same. So we've got the integral from 0 to a. I haven't actually changed the variables, so if we want to have a go at changing the variables here, it is going to be quite the same, but let's prove that. So u is equal to a minus x, which means when x is 0, u is going to be a minus 0, which means that that's going to be a there. And when x is a, u is going to be a minus a, which is 0, so that's there. So we've kind of flipped the bounds here. So let's flip them again and get rid of that minus. This is the integral from a to 0 to a of f of u du. which is the same as the integral from 0 to a of f of x dx, because it's a definite integral. We're finding an area. If we change the variables, it doesn't change anything as long as the bounds are the same. So we're going to use that to find the integral from 0 to pi of x sine of x dx. I'm just going to rub this out to save space. When I print out the booklets, I'll print them out one-sided, so we'll have the other page. So find the integral from 0 to pi of x sine of x. Well, we've been shown and we've proved that transforming this function means the same thing. So we could say that this is the same as saying the integral from 0 to pi of pi minus x. And notice we're going pi minus x because that a is the same a from there. So that pi is going to go here, sine of pi minus x dx. Now if we expand that, that's going to be the integral from 0 to pi of pi sine of pi minus x minus the integral from 0 to pi of x sine of pi minus x dx. And we know as well, well, if we think about our all stations to central, sine is the same in the first and second quadrants, which means pi minus x, sine of pi minus x, which is the same as 180 minus x, is just the same as sine of x. So we can say that the integral from 0 to pi of x sine of x, which was our original question, dx, is equal to the integral from 0 to pi of pi sine. Now we've just said that pi minus x is the same as sine of x. So this is sine of x minus the integral from 0 to pi of x sine of x. Again, we've just said that sine of pi minus x is the same as sine of x because sine is positive in the second quadrant. So let's plus this over to here. So this is equal to 2 lots of the integral from 0 to pi of x sine of x dx, which is equal to which is equal to the integral from 0 to pi of, we might take the pi out as a constant, because remember pi is just a constant, x dx. So let's divide the 2 over to here. So we've got a 2 there. We don't care about 2 lots of the answer. We want to know what 1 lot of the answer is. So divide that over there. So this is pi on 2. The integral of pi is minus cos. So minus cos x from 0 to pi, which is going to be pi on 2 times minus minus 1 minus 1, which is 2. So that's that there. I think I did too many steps in one there. I might quickly show that. So minus, now cos of pi is minus 1, minus minus cos of pi, which is 0, which is 1. So that's 2. The answer is pi. Example number 2 is we're finding the integral from 0 to 1 of 1 minus x to the 99 times x. Now there's probably a lot of ways of doing this question, but I personally would be most comfortable in using a u substitution. So I'm going to say let u equal 1 minus x, which means du is minus dx. And from that we can deduce that x is 1 minus u. While we're doing that, we might change the bounds as well. So when x is equal to 0, u is equal to 1 minus 0, which is 1. And when x is equal to 1, u is equal to 1 minus 1, which is 0. So we're finding the integral now from 1 to 0, of 1 minus x is u, so u to the 99, times by x is 1 minus u. Now we want a minus dx to replace the du with, so we need to put a negative out the front and make that du. That would make this dx negative. we make the dx negative, and to account for a negative we need to introduce a double negative to get rid of that negative. So we put a negative out the front because two negatives make a positive. So this is minus the integral from 1 to 0 of u to the 99 minus u to the 100, which we could say is the integral from 1 to 0 of u to the 100 minus u to the 99 du, which is u to the 101 over 101 minus u to the 100 over 100, but this time we're integrating from 0 to 1, so the 0 will cancel and it's going to be minus 1 over 101 minus 1 over 100, which is 1 over 101 100. That's the answer. Okay, last couple of examples. We're looking at the integral from minus a to a. Now, minus a to a is kind of the same, so we're thinking, oh, maybe it's 0 or maybe it's two lots of something. But I do know that this is equal to a half of sine of 2x, because 2 sine x cos x is sine of 2x. And sine of 2x is sine of 2x, sorry, is an odd function. Sine is an odd function. And if we integrate an odd function from the same magnitude bounds on either side of the y-axis, we get 0. So the answer to that is 0. Alright, last question for today is the integral from 0 to pi on 2 of tan of x minus pi on 4 sec of x minus pi on 4. Now, integral tan x sec of x, if we integrate that, we will get sec of x. So we could do that, or we could realise that tan of x is an odd function, and sec of x is actually an even function. And that's because sec is 1 over cos, and cos is an even function, and 1 over an even number is still an even number. Say 1 over 2 is an even number. So 1 over an even function remains an even function. Not necessarily, 1 over an even number, but 1 over an even function is still an even function. And an odd times an even is an odd. So therefore, tan x sec of x is odd, which means the integral from 0 to pi on 2 is equal to, so the integral, we know the integral from minus pi on 4 to pi on 4 of tan x sec x is equal to 0, but this function has been moved this way by pi on 4. It's been transformed by pi on 4. So if we add pi on 4 to each of those and transform the function, we get the integral from 0 to pi on 2 of tan x of x minus pi on 4 sec of x minus pi on 4. So we've just transformed that function across the x-axis, and therefore it's 0. Okay, thank you for listening.